was hoping for a few minutes to sort of gather my thoughts before we started, but what the hell. Right. So first of all, let me give you a bit of background to the experiment. It's a bit different from the ones that you've been doing previously, because what we're trying to do is give you an example of what it's like to be a PhD student in physical chemistry. Most of the laboratory experiments we've done so far have been sort of the Jamie Oliver type of experiments. Pour everything into a pot, mix it up, it turns out to be a nice colour if you're lucky, if it doesn't, you did it wrong. Just following a recipe. What we wanted to do with this experiment was give you something that was very open-ended, something where you won't get all the answers aren't obvious. You have to think about things, put things together, try and come up with your own solutions. There may be different solutions from the ones we get. That's fine. So what we've done is we've given you two sets of data that was recorded a couple of years ago by PhD students in physical chemistry for an experiment which was published shortly afterwards. Your job is to try to interpret the data and reach whatever conclusions you can, as many conclusions as you can about the data. Now, there are questions in the manual to guide you about the sorts of things you should be answering. There's lots and lots of information there that you might be able to get in addition to that. Don't expect you to get it all. Most people don't. In fact, nobody's got all the information that I think is there yet. It is a hard practical, as I'm sure you've gathered from talking to your friends. Don't expect it to be easy, so you need to start straight away. Come and ask me questions, and I hope that you'll enjoy it. So, the experiment that you're looking at is the absorption of phenol iodide onto a copper 110 surface. And we know a lot about the copper 110 surface, and that information is in the booklet. Don't forget that that's there, you can use that. The reason we're studying it is that we are interested in a catalytic reaction where phenol groups are coupled together to form biphenol. And that's done over a copper surface. So we're looking to see if we can see what's happening on the surface when they're coupling. Can we work out the mechanism? And if we can understand the mechanism, then we can work out ways to make the reaction faster. We're studying the reaction at the atomic molecular level. So we're looking at it under conditions that aren't truly catalytic conditions. We're looking at it under ultra-high vacuum with a dirty great spectrometer, and I'll take you to see the spectrometer a bit later. And there's no chance of you doing that real experiment by yourselves, which is why we've just given you the data. However, most of physical chemistry is about interpreting the data anyway. Okay, so we're using two techniques to study it. The first technique is X-ray photoelectron spectroscopy, and you will have met that a little bit, but I'll just remind you of the basics, because I don't think you've done it in as much depth as I would like you to have done. You may have to look that up on the web or in past lecture notes. I think Adam talked to you a bit about it in the CH2210. Okay, so X-ray photoelectron spectroscopy, we fire X-rays at a surface, the X-rays ionise the atoms that are at the surface, the electrons that are produced come out, we measure their kinetic energy, and that kinetic energy combined with the photon energy tells us about how strongly they were held in the atom on the surface. It's sort of the ionisation energy, and as you know, the ionisation energy is a fingerprint of the element. So by measuring the binding energy, is what we call it, by measuring the binding energy, we can determine what elements are present on the surface. It's surface sensitive because the electrons can only travel a short distance through the solid. It's also quantitative because the number of electrons produced is related to the number of atoms that are on the surface. So we can calculate how many atoms and of what type are present on the surface. The way you do that calculation is you take the area of the peak and multiply it by a factor which we can work out, which is given to you in the manual. Taking areas of peaks is a bit of a problem. It's a little bit hairy, and you've got enough to learn with this practical. So instead, we're going to take a simpler route and For this practical, all you need to do is measure the heights of the peaks. That wouldn't be appropriate if your peaks had moved at all, because then the peak might be broader and still have a large area. It would be low, still have a large area, but because it's broad, it's low, and your concentration wouldn't work. But in this case, I know that your peaks are all in one place, and so you can use the height as an effective measure of surface concentration. You'll be measuring the height of the carbon and of the iodine. There's things to say about both of them. The carbon spectrum is quite noisy. You'll see that the signal looks like this, and you'll be tempted to measure the height, well, perhaps it'll be a little bit, so you'll be tempted to measure the height of peaks which aren't really there. So be a little bit careful about that. Convince yourself there is truly a peak to measure the height of. Don't just measure the height of noise. So that's the carbon region. The iodine region you've got to watch out for as well, because the iodine region's got two peaks. Look at it like this. You don't need to film that bit. We'll add this to slides later on. Okay, the iodine region looks like that. There are two peaks, and the reason for that is that you're looking at the iodine 3D. And the thing about the 3D is that it's got orbital angular momentum, and the electron spin can interact with that. And it will either be aligned parallel or anti-parallel, and that gives you the two peaks. When you measure the concentration of the iodine, you're only interested in the height of that first peak. It's that height of that peak you're interested in. It's called the 3D 5/2, that peak. Right. The data is saved as an Excel file, so you can call it up in Excel and use Excel to measure those peaks and display them for your report. Okay. The most important thing to keep in your mind is the XPS tells you what's on the surface. It tells you what elements are present, it tells you how much. And throughout your analysis, you've got to keep that in mind. Refer back to the XPS every time. What's on the surface at this point? That will help you to interpret the next set of data. I should tell you as well that what happens during the experiment is we start off with a clean surface and we expose it to progressive amounts of phenyl iodide. And the units we use are Langmuir's, so you will see that a particular spectrum was run at 30 Langmuir's. And then one that was run 100 Langmuir's has had another 70 Langmuir's added on the top. Okay. Now, the really fun part is that you're now going to look at the surface at atomic resolution. And to do that, we use a technique called scanning tunneling microscopy, which I know you've heard about. Okay. So, on the disk, you'll find the data from those images, and you'll need to use a program to analyse the images. So the program we're going to use is also on the disk. If you go onto the disk, into the directory for the STM-XPS experiment, you'll see three directories. One's got the XPS data, one's got the STM data, those are the pictures, and one's called WSXN, and that is the program you will use to analyse the images. And I need to explain to you a little bit about the program so that you can use it properly.